All right, happy April Fool's Day. This is the second time in my teaching career that I've accidentally played an April Fool's joke on myself on April Fool's Day. If you want to know about the first time, you can ask during the Q&A, but just a while ago I started making this video and I was just running right along. I've got about a minute into it and I looked down and I wasn't even wearing a microphone. I was talking to nobody, and so I had a video with no sound. That didn't do any good. So anyway, great start. Let's see if this lesson can go a little bit better. This is going to be a two-day lesson I'm going to put into just one video, so you can take a break about halfway. I'll try to let you know when we're about halfway done so you can take a break. But we're starting chapter 6. We're just going to start it. That's as much time as we're going to have this school year, and it's over applications of integration. So all of this integration that we've been talking about with the fundamental theorem of calculus, the definite integrals, the indefinite integrals, and the U substitution, all of that, where does it play a role in the math world? Well, we can do a little bit more with areas than we've already done with the definite integral. Okay, so we can actually find the area between two curves. So I'm just going to make up two curves. I'm going to have a blue curve just hanging out right here. We'll call it F, and we'll have a G curve down here. And so what we have already done is we have found the area underneath this F curve, right? We took all these approximating strips. We did midpoints, we did left endpoints, we did right endpoints, and we were able to find the area by just doing a ton of these approximating strips going down. Well, if I have two curves going at once, and suppose that I come over here and just do the area underneath this G curve right here. Suddenly, I have some overlap there, and what I am left with is this area right here on this approximating strip that is between my curves. And so if I get enough of these lined up going across, I can find out what the area is between my two curves. Now, each width is still going to be delta x. And so writing out what this area would be, well, I'm going to take the limit as n approaches infinity, because I still want an infinite number of these curves right here, or strips between the two curves. And I'm going to add up the area of each strip. And the big kicker on this is making sure that you are using f of x minus g of x. Whether you're using left endpoints, right endpoints, or midpoints, that's why I put that I in there. It'll take care of that. And so I've always got to make sure I'm doing the top curve minus the bottom curve. Now, surely we have a shortcut for this because we have a limit of the sums. And we know that any time that we have the limit of the sums, recently we've been able to do an integral with it. So more formally introduced, okay, all this that I'm erasing right now, it can be described as the area of the region bounded between two curves, f and g, where the lines x equals a and x equals b are going to be the bounds. If they're both continuous and f is bigger than g, then yeah, we can just rewrite everything as the integral from a to b of f of x minus g of x. And then my delta x will change to a dx, just meaning a little bit of x, since delta x is going to be getting smaller and smaller. So let's try this with an example. I want to find the area of the region bounded by these two parent functions. We know these two parent functions. We're good with them. We have y equals e to the x. That's just the exponential function that comes up. And then we have y equals x. That's the identity function that runs through the origin and has a slope of 1. And what I am wanting to do is I'm wanting to find the area of the region that's between 0, and I'm just going to make up a spot right here, 1. So I'm wanting the area between right there. And again, just over teaching this just for a second, I'm going to find the area, all the area that's underneath this green line, and then subtract off all the area that's underneath this black line. What that will leave is the area that's in this blue shaded region. Okay. So let's give it a go. So I am going to set up my interval, and it's just my left bound and my right bound. My left bound is going to be my lower limit of integration, while my right bound will be my upper limit of integration. And then I always want to do top minus bottom. The top line is just y equals e to the x. You can tell that plainly right here in my drawing. And I'm going to subtract off my bottom line. My bottom function in this case was x. So U substitution is fair game on all this. A lot of these, though, we won't be using U substitution on, so it's going to be very rare when we do that. Instead, I'm just going to integrate this. Take the antiderivative of e to the x. That gives me e to the x. Take the antiderivative of negative x. That gives me negative 1/2 x squared. And that is going to be evaluated from 0 to 1. So plug in my upper limit. That gives me e minus 1/2. You might be thinking you're getting off the hook. Hey, I plug in 0, everything goes away. It doesn't go away. E to the 0 gives me 1. This part is 0, so that's going to give me e to the negative 1/2. Whatever that would be as a decimal, that's fine as well, but you know how I feel about exact answers. I love them. Okay, let's up the ante a little bit. This time I'm not going to tell you what the left and right bounds are. I'm just going to tell you both of these are parabolas, y equals x squared and y equals 2x minus x squared, and I want you to find the area between them. So y equals x squared, remember that's just this nice even parabola coming up, put a little bit too far to the left, it'll be okay. And you might need some help with a graphing calculator on this, okay? I see that it goes to the point 0, 0. If I plug in 0 in for x, x is, I do get a 0 for y. And it faces down, so it's probably going to look something like this. And I'm wanting to find this area that is enclosed right here, that green area. Well, the problem is, I get to here, and I see that it's going from 0 to something. I just don't know what that something is. Well, if y is equal to x squared, and y is equal to 2x minus x squared, and I'm wondering what x is, since they're both equal to y, I can do a substitution and plug both of them in. I'm just going to bring everything over to the left side. So I'm going to add the x squared, subtract off the 2x, set equal to 0. All I can do to factor this is pull out a GCF. So I get 2x equals 0. Well, that would just give me, switch colors down here. That just gives me x equals 0. I already knew that. I already knew that x equals 0 on that side. But over here, this gives me x minus 1 equals 0, making it so I know what my right endpoint is now. It has to be 1. So those are the points that they share in common that bound this green region. So I put my 1 up here. Then I just want to make sure I'm doing top minus bottom. Look at what's on top. The blue line right here is on top. Remember, the blue line was this upside down parabola. So it's going to be the 2x minus x squared minus my regular parabola, my parent parabola that is sitting at the origin, which is this y equals x squared. So I got a little bit of cleanup to do on this. I'm going to go from 0 to 1. Let's see, I've got 2x minus 2x squared. Hey, I have a GCF in there. You see that GCF? You can definitely pull this 2 out in front if you want to. If not, I'm just going to roll through with the integration on it. So that's going to give me an x. That's going to give me a 2/3 x cubed. Ooh, that gives me an x squared. I'm sorry. So raise the exponent by 1. That'd be a 2 over the new exponent. Yeah, definitely x squared. So I'm evaluating this from 0 to 1. I luck out when I plug in 1. I just get 1 minus 2/3. I just get my coefficients in front. And whenever I plug in 0, yeah, this time you do get lucky. It just turns into 0. And so if I do 1 minus 1/3, that does give me the area of this green region right here, which is simply 1/3. let you guys start this one. I want you to go ahead. I'm not going to tell you the left and right bounds again. I want you to go ahead and find the area, not the area, the intersection of these two. I don't know what they are. Well, this one looks like a parabola because I see the x to the fourth. But I'll let you guys go ahead and have at it. Okay, so hit pause on the video, and you can come back and see what my intersection is versus yours. You are probably where I am on this problem. I multiplied both sides to get rid of fractions. It just didn't go anywhere. So we're going to need to use the help of our graphing calculator on this problem. Okay, so got my graphing calculator ready to go right here. And so how I'm going to find the intersection on this is, let me try to turn my lights back on, see if that helps. I'm going to try to find the intersection on this by just plugging in the two y equals that they gave me in the problem. Okay, I'm going to go ahead and just graph everything out. And so whenever I hit graph, I have, this is my first function, that crazy one that has a square root in it. And then there's my parabola, that x to the fourth function. Okay, it graphed them in the correct order, so I was able to get those. Okay, and so I'm looking for this little bitty area right here. Well, I see one of them looks like they cross at 0. I can make sure of that in just a minute. But I'm just not sure where that one is crossing. And so to figure out where that is, I'm going to hit second calc. And this will work on your iPhone as well. So if you have that graphing calculator app on the iPhone, it'll easily do all of this as well. I already tried it. Okay, and I'm looking for the intersection between this blue curve and this red curve right here. And it's going to make a guess for me. And there it is, 1.18 looks like is where I am unfortunately landing. And so this one is going to turn out to be 0, 0 if I was to plug that in. So we need that 1.18 though in order to continue this problem. So I'm going to make the long journey back up to the front of the room, and both of my smart pins are in the back of the room. So I'll make the long journey back up to the front of the room again. And so my area is going to be the integral from 0 to 1.18. Again, this wasn't a nice parent function right here, and this one really wasn't either. So using a graphing calculator to help you find the intersections on this, totally fine. Okay. Now looking at it, this blue function that it graphed first was on top. Ooh, how are we going to integrate that? And then I'm going to subtract off the red function that was on the bottom of that shared region. All right, this does not look like fun, but we will tackle it. All right. Now remember one of my, I put that in the wrong spot. So remember one of my my integral properties says that I can easily take the integral of both of these. Okay, so I'm going to take the integral from 0 to 1.18 of what you're going to hear me refer to as the hard part, dx. dx goes with both of them. And subtract off, I'm going to take the integral from 0 to 1.18 of what you're going to hear me refer to as the easy part. So on this harder part, I'm looking at it, I don't know of anything that looked like any of this. And so I'm going to have to go back to my u substitution. Like I said, that was going to be fair game. So I'll look and see what's inside the function. It's u equals x squared plus 1. So my du would equal 2x dx. I love having the x on it. I don't love having the 2. All right. So that will allow me to rewrite all of this. And I'm also going to change my endpoints. I'm a fan of changing the endpoints. If I plug in 0 in right here, I get 1. And if I plug in 1.18 in for x, I get 2.39. So I'm going to go ahead and change my endpoints as well. Okay, so that's going to make it so that the nasty part of my integral, the nasty side, is going to be, well, let's see, the x and the dx will cancel with a 1/2 in the du. So I got the 1/2 and the du going on. And the only thing I'm left with is 1 over the square root of what I plugged in for u. Well, 1 over square root of u is the same as u to the negative 1/2. So my nasty part doesn't look quite as nasty anymore. And we still have the fun part over here, 0 to 1.18. Okay, so bring down the 1/2, and I'm going to raise the exponent by 1. That's going to give me u to the positive 1/2 divided by 1/2 is the same as multiplying by 2. That's good news. 1/2 and the 2 is just going to cancel. And I will then be able to evaluate that from, I have to bring down my endpoints, 1 to 2.39. Minus the easy part, 1/5 x to the 5th minus 1/2 x squared. Now this one's going to keep the same endpoints because I didn't change it to a u. So now I get just to plug everything in. I get to take the square root of 2.39, subtract off the square root of 1, bringing down this minus sign right here. I'm going to be a little bit careful with my signs over here, but I'm going to have 1.18 to the 5th over 5 minus 1.18 squared over 2. I'll just tell you, I made my calculator do all this, and I got 0.78461. This should be the area between these two curves. That's about as hard as I can make it. So don't think that we're just going to kind of go off from this. But that's, if I'm using a graphing calculator, it's because there's going to be some difficulty in it. So a couple more shortcuts that you can definitely, that I can show you on this, that you can ask about during the Q&A if you are interested. Okay. Let's see a Riemann application of this. Okay, we're not even given a formula on this. We're just told that this figure is showing the velocity curves for two cars. So cars A and B start off right here, and they take off from the same spot side by side, and they're going down the same road. Now car A, it looks like it's going a lot faster than car B is at every second that it goes down the road. So if I was to just find the area between these two curves, what would it represent? Well, the area between the curves would just be if I was to take the antiderivative of the velocity. So the area between the two curves, what does it represent? It has to represent the distance between, my handwriting's going bad. Let's clean that up. Between the cars after 16 seconds. Okay, distance between the cars after 16 seconds. And then it wants me to estimate it. Estimate what this blue area right here is. Well, look, I'm not just doing area underneath. To get my hands on this blue area, I'll just tell you, I'm going to use delta t to be 4. So if I'm estimating what that blue area is, and I'm letting my first rectangle come this far, I'm going to have to find out, I'm going to use midpoints, it says. I'm going to have to find out what the area is of this box, and then I'm going to subtract off the area of this box. There's a little bit easier way to do it, because if you look at the difference between those two areas, it's just going to be the length of this black line right here. Okay? And so my delta t is going to be 4. So the difference, to find out what the area of this black box right here is, it's going to have a width of 4. I just need to find out what its height is. All right, so let's erase this real quick. I need to find out the difference in their velocities. That will tell me the area between the curves. And so the first one, going from 0 to 4, it looks like the difference in their velocities is, I'm going to call that about 10 miles per hour. I'm going to call that about 23 down to 13. Might be 24 to 13. I'm just going to use 23 to 13. So let me get rid of some of this clutter because we have a problem. Problem is they told me how fast the cars were going in miles per hour. And down here, I'm in seconds. I'm not in hours. These units need to match in order to go forward. So I'm going to start something on another screen real quick. And we're just going to kind of go back and forth for a second, so bear with me. So I'm wanting to integrate from 0 to 16 of the difference between the velocity in car A and the velocity in car B, delta T. And so that's going to be able to be approximated by, well, I'm going to go ahead and bring my 4 out in front. Remember I said that each width right here was going to be 4? I'm going to bring that 4 out in front. And I need my units to match. I said that the car was going 10, or the difference in their speeds was 10 miles per hour. Well, I need it to be in seconds. So I'm going to try to do this the way Mr. Myers does. I'm going to change that 1 hour, I'm going to change it to 3,600 seconds. Okay, let's do a little bit of foreshadowing what's going to happen. Yeah, my hours are going to cancel, but now I've got such an insanely small number, 10 divided by 3,600, that's going to be tough to work with. So if I'm changing everything to seconds, I'm going to go ahead and take one more step and get rid of my miles and change it to feet. Because the difference in the cars after 16 seconds isn't going to be a matter of miles, it's probably going to be a matter of feet. And so 5,280 feet in a mile. I know that thanks to Remember the Titans. Okay. And so if I do this math right here, 10 divided by 3,600 times 5,280, that gave me my first height to be not 5, still on the 5,280, 14 and 2/3. Okay. Okay, let me go back. Oh dear, that's not back. That doesn't go away either unless I go back and get rid of it. 1 second. Okay, so let's go back. Got off a little bit somehow. Let me here. Back. There we go. Now I'm back on. So I'm ready to do my second box. Now my second box is going to run from 4 to 8, making my midpoint 6. Really, I just need this distance between their velocities at 6 seconds. I said that that distance was 16 miles an hour. So I'm going to go back and get rid of this 10. And I'm going to put a 16 miles per hour in there and change that to feet per second. And it gave me 23.47. Okay, let's go again. Let's go back. Control remembering which way was back. Again, from 8 to 12 right here, the midpoint is 10. So the difference between their velocities at 10, I got to be about 19 miles an hour. If you think it's something different, you can definitely use that. But now I'm just going to plug in 19 miles an hour and change that to feet per second. And that gave me 27.87. Got one last one to do. Again, I'm having to, I keep thinking it's forward. I should have made it so they're all forward. Remember, I'm having to do this because my hours and my seconds didn't match. Hopefully in the homework they might match. My last interval right here goes from 12 to 16, making 14 in the middle. My difference at 14 miles an hour, I have the cars going, I'm sorry, at 14 seconds, I have the cars going 20 miles per hour difference is what it looks like. So I'm just going to change this number just a little bit to 20, and that ups my final one to be like 29.33. So I end up doing a Riemann sum on it. It's just that your height has to be the difference between them. It has to be the area in between. Okay, so I haven't done this math yet. So I'm going to take, let's see, 14 and 2/3. I'm just going to call that, I'm still on the graph, 14.67 plus 23.47 plus 27.87 plus 29.33. That gave me a big number. Multiply it by 4. There should be around 381.36 feet between the two cars at 16 seconds. If you're looking for a good spot to call it a day, this is a good spot to call it a day. You can go to the end, see what your practice problems are, and do a couple of these. Okay, I'm going to go ahead and continue and just make this so it's just one video, and go ahead and start day 2 now, and see what happens whenever one curve's not always larger than the other curve. Okay, this is going to happen on one of your upcoming assessments. I remember the problem. I don't remember if it's a quiz or a test, but this will happen. So looking at this, my f of x curve, it starts off a little bit higher than my g of x. That's what we're used to. But something happens right here at this point. My f of x is now smaller than my g of x. And then it flops back and forth. And so in order to remedy this, what I'm going to have to do is I'm going to have to find this area with my red curve on top of my blue curve, red minus blue, and then find this area, and I'm going to have to do blue minus red, and then I'm going to have a cutoff point here. I'm going to have to do this area, this third area, this third section, and I'm going to have to go back and do red minus blue on that one. It's confusing. It goes back and forth. Let me show you an example. Think about a curve that would go back and forth and alternate between the two. Yeah, it's going to be f of, oh, we're not ready for an example yet, my bad. If this does happen, if I'm looking for the area between the two curves, what I'm going to have to end up doing is I can still do f of x minus g of x every time. I just need to make sure I'm getting a positive answer. Anytime, you shouldn't have anything negative anytime you do the area between two curves, whether it's above the axis or below the axis. It should always be positive. But you're going to have to break this up. Okay? And so let's see how to do that. All right, so I'm wanting to find the area of the region. So yeah, curves that sit there and will oscillate back and forth over each other are going to be the sine and cosine curves. So let's draw them. We're going 0 to pi over 2. So I'm going to graph the sine curve in blue. So the sine curve starts up, comes down. That's all the way to 2 pi. I'm not wanting to go that far, but I'll shrink it down in just a minute. And then the cosine curve, graph them on the same one. Wish me luck. Here we go. I'm going to go ahead and draw me some guidelines here. Here, here. It's going to come down, and it's going to come back up. Now, like I've already said, I'm not interested in 0 to 2 pi. I'm not even interested in 0 to pi. I'm interested in 0 to pi over 2 right here. So this small section that's between the y-axis and this black line right here. And so I'm going to call these sections, I'm just going to call them S1 and S2. Or you can do A1 and A2, it doesn't matter. But my area between those two curves, I'm going to have to split this up. Now, first of all, I'm going to need to find out what this magic point is in the first quadrant where sine and cosine take on the same value. Pi over 4, right? Sine of pi over 4 is square root of 2 over 2. Cosine pi over 4 is square root of 2 over 2. So I'm just going to do my S1 first. And so whenever I do my S1, I'm just going to go from 0 right here to pi over 4. Now looking at that region from 0 to pi over 4, my green line's on top. Well, my green line is my cosine. And so I'm going to have a cosine x happening right there. And then what's on bottom is my blue line. My blue line is sine of x because it came up from the origin. So I'm going to subtract off sine of x dx. Good news there, it doesn't look like I have any u substitutions on it, so we like that. But I'm going to need to add that to the area of the S2. Now the S2, looking at it, it goes from pi over 4 to pi over 2. So my lower bound is pi over 4. It's going to grow to pi over 2. And it's just the opposite on this one. On this S2 right here, in this region, my blue line is on top. So this time I'm going to do sine x minus what's on bottom is my cosine x. I didn't leave room for my dx. So I have two different intervals. Luckily, it's not going to be as bad as last time I had two intervals because I had a nasty equation on there. But if I want to integrate cosine x, let's see, what do I take the derivative of in order to get cosine x? Well, that's going to be sine x. Let me not use blue because that's sine x. If I take the derivative of positive cosine x, I get negative sine x. So that's good. There's that part done. Plus, should have about the same thing right here. So the derivative of negative cosine x should give me positive sine x. And if I take the derivative of negative sine x, that gives me cosine x. So as you can see, there's going to be a difference in signs between these, and that's the reason why I have to split it up twice into two different intervals. And I'm still going from pi over 4 to pi over 2 over here. All right, get the fun part. Plug it in. So if I plug in pi over 4, well, it's just going to give me square root of 2 over 2 plus square root of 2 over 2. And if I plug in 0, that's going to give me 0. I mean, cosine of 0 is 1. Careful with that. Bring down my plus sign. All right, let's plug in. I got to do the top bound first. So pi over 2, cosine of pi over 2, that's going to be negative 0. Let's just call that 0. And then minus sine of pi over 2, well, that's 1. Okay. And then I'm subtracting off the lower bound plugged in, where there's those square root of 2 over 2's coming in. So I got negative square root of 2 over 2 and negative square root of 2 over 2. All right. Oh, so let's just take a step and get rid of parentheses. Square root of 2 over 2 plus square root of 2 over 2 minus 1 minus 1 plus square root of 2 over 2 plus square root of 2 over 2. So how many square root of 2 over 2's do I have? 1, 2, 3, 4. I have 4 square roots of 2 over 2. And then I have negative 1 and negative 1 is negative 2. So that's going to give me 2 square roots of 2 minus 2 for that area. Might have some questions on that. Find some like that in your practice problems, and we can definitely work on that during our Q&A later. Well, there's one other wrench I can throw in. Man, always leaves just a little bit. What if I was to not have a function of x? What if I have a function of y? What if I have a function of y here, and then I have another function of y here? Okay? And so, I should have color coordinated that. Got it. We got it. I don't know if it looks the same or not. It doesn't matter. So, this is my f, and this is my g. Well, it's going to be really hard to do my approximating strips unless I do my approximating strips this way. Well, that means that instead of having a delta x, I'm going to have a delta y. And instead of having bounds on the left and right, I'm going to have a lower bound, going to be c, and then an upper bound up here, if I just cut it off the top right there, is going to be d. And so I can still find the area between the curves. It's just now I need to run all my approximating strips going left and right. So what does that do to my area equation? Well, that means I'm going from C to D. Notice I'm going, again, from the smaller one to the bigger one. And then I've got to do my greater function first. I don't have a top and a bottom, but this f function over here on the right, all those values should be bigger than the ones over here that are to the left. So I'm going to do my right function minus my left function. Uh-oh, you guys see what I did wrong? My left function of y. Remember, these aren't going to be functions of x's anymore. They're going to be functions of y, meaning that I will have a dy out here. Okay. Last example, let's try this. Okay, so I have y equals x minus 1. I'm pretty sure I can graph that. Y equals x minus 1. That's just going to be a graph that goes through negative 1, has a slope of 1, goes up to the right. There's my blue one. My red one's going to be y squared equals 2x minus 6. Well, we graphed this last year. It was at the end of the year. And so we said that its vertex would be at negative 3, 0. And then since this p value right here is positive, it opened to the right, I'm just going to do a rough sketch of it. And so since it was y squared, it didn't open up or down. It wasn't a function. It opened to the right. And so I'm wanting to know what this area between these two curves is going to come out to be. They didn't tell me any intersections. Okay? And so I want my intersections to be my upper and lower limit of integration. And so my intersections, if you look on this one, are at the top and the bottom. It's not over here at the left and the right. The right one would still work, but this guy being on the bottom means that I want everything in terms of y on this. So I've got a little bit of work to do on this. And so to find out what my intersections are, I'm just looking, they're both pretty much almost solved for y. I can do a little bit of work here. I can do y equals be plus or minus square root of 2x plus 6. And so using that same technique that I had a while ago, I can find out what those x intersections are. So let's go ahead and do that and see where we end up at. Okay. Solving this all the way down for x, I got x squared minus 2x plus 1. And then subtract off 2x, subtract off the 6. I should get something that's factorable. If it's not factorable, it's going to be a little bit tougher. So I get x equals 5, and I get x equals negative 1. What does that tell me? It tells me that this coordinate right here is going to be 5 something. Well, to find out what that something is, just plug it in for x. Hey, better yet, plug it in for this x. They're both the same. They will give you the same answer. And so 5 minus 1 is going to be 4. Negative 1 minus 1 is going to be negative 2. I would have got the same thing if I would have plugged it in right here. Just might have had an extraneous solution on it. Okay? And so that tells me that all of my approximating strips over here on the axis is going to be running from positive 4 right here all the way down to here, which is negative 2. So my area is going to go from -2 to +4. Now, the next thing to keep in mind is that I want functions of y on this. Okay, well, that's not going to be too hard to switch my blue one up here. I'm just going to add 1 to the other side, and I get x equals y plus 1. Now, my red line, if I bring it down, I'm wanting to solve it for x. And so I get y squared minus 6 equals 2. And so that's going to give me, I'm just going to divide everything by 2. And just call it 1/2 y squared minus 3 is equal to 2, I'm sorry, x. Okay, so my functions have to be in terms of y because each of my approximating strips that I'm making in here are stacking up in the y direction, delta y. I got to do right minus left on this, so my blue line right here is going to be my right bound. My right bound is y plus 1. And then I'm going to subtract off my left bound. My left bound is my red line, which came out to be -1/2 y squared minus 3. And this is all dy instead of dx. That won't really change much. I'm going to do a little bit of cleaning up on this before I get going. So I'm going to make it a decreasing function. So I'm going to bring that -1/2 y squared out in front. And then I have a positive y. And I got 1 minus a -3. I'm going to go ahead and call that 4. This will be a little bit easier to integrate. I won't have as much stuff to integrate on this one. Okay, so finding this area, I'm going to raise this exponent by 1. It's going to be y cubed. Put it over the new exponent. That's going to be -1/6. Okay, 2 times 3 will give me that 6. Raise the exponent by 1. Put it over the new exponent. Raise the exponent by 1. Put it over the new exponent. So I'm going to plug in 4 in for everything. Well, when I plug in 4 right here, it's going to give me 4 cubed. Let's see, 4 times 4 is 16. 64. -64 over 6. And then I got 4 squared is 8. I'm sorry, 4 squared is 16. Half of that is 8. And then 4 times 4 is 16. I'm going to go through and I'm going to plug in -2 in for everything. So -2 cubed is -8. Positive 4/3. I think that's what I got. -2 squared is 4. Half of that is 2. And that's going to give me a -8. You check that 4/3 again. So -8 over 6 over -6. 4/3, yeah. So put all that in my calculator. The area of this whole green shaded region right here, there's a lot there, is going to be 18 square units. It will obviously take some practice. And if you can get good at this, it's going to make our last 2 sections so much easier. Because what we're going to do in the last 2 sections is we're going to be doing volume. So we're going to be taking these areas and we're going to be spinning them. So we're going to have the same first step in the last couple sections that we're doing right here in these type of problems. Here you go. You should have a good while to work on this. If you have questions, put stars by them, guys, and we need to hash some of these out together, and we'll do so, okay? Have a great rest of the day, and I'll see you guys next time.